Hey everyone, welcome back. Today we are tackling one of the most misunderstood topics in system design interviews, consistent hashing. And I say misunderstood on purpose because almost every candidate I talk to has heard of it. But when you ask them to actually explain why it exists or walk through what happens when a server gets added, most of them freeze up. By the end of this video, that's not going to be you. We're going to build this up from first principles, the actual problem it solves, the hash ring, virtual nodes, and a nuance almost nobody talks about that separates strong candidates from great ones. Let's get into it. Let's start with the naive approach because you need to feel the pain before the fix makes sense. The obvious way to distribute data across servers is take your key, hash it, and mod by the number of servers. Hash of key mod n. Dead simple. It works great. Right up until your server count changes. And in any real system, it changes constantly. Servers crash, you scale up for traffic, you scale down to save cost. Here's the problem. The moment n changes, say you go from 3 servers to 4, that modulo operation produces a completely different result for almost every key. Watch this. With mod n hashing, adding just one server can remap something like 75% of your keys. Think about what that actually means in production. Massive cache invalidation, a flood of database reads, latency spikes, maybe even downtime, all from adding one server. That's the problem consistent hashing was built to solve. Let's put real numbers on this because cache invalidation can sound abstract until you see the blast radius. We just saw that adding one server to a naively hashed cluster can remap around 75% of your keys. Now think about what happens next. Every one of those remapped keys is now a cache miss. Your cache layer, which exists specifically to protect your database, suddenly isn't protecting anything. That's how you get a 10x spike in database load, right when your system was already under pressure from a scaling event. This is literally the cache stampede problem, and it's happened at real companies in real production incidents. And here's the frustrating part. The ideal number of keys that actually needed to move when you only add one out of many servers is close to zero, maybe a small fraction. So the entire cost we just described is completely avoidable. That's the promise of consistent hashing, and that's exactly what we're building toward. So here's the actual insight behind consistent hashing, and it's a really elegant one. Instead of using modulo to force a key into a fixed range based on however many servers you currently have, imagine your hash space isn't a straight line, it's a circle. Here's why that matters. A 32-bit hash only produces values between 0 and 2 to the 32 minus 1. If we laid that out as a straight line, a key hashing near the maximum value would have no server sitting to its right. So instead, we bend that line into a ring. The highest point connects right back around to 0. That way, walking clockwise always finds the next server, no matter where you start. Now, here's the key move. We hash the servers onto this same ring too. Server A, server B, server C, each one gets hashed to some point on the circle based on something like its IP address or server ID. And keys get hashed onto that exact same ring using the exact same hash function. So now both your data and your servers live in the same coordinate space. That single decision is what makes everything else about consistent hashing work. Let's see how keys actually find their server next. Okay, so now that both servers and keys are points on this ring, how does a key actually find out which server owns it? The rule is beautifully simple. You hash the key, that gives you a point on the ring. Then you just walk clockwise from that point. And the very first server you run into, that's the owner. Look at this example. Key user 42 hashes to a point right before server A, moving clockwise. So server A owns it. Order 99 lands right before server B, so server B owns it. That's it. That's the entire lookup algorithm. No modulo, no dependency on the total server count. Just walk clockwise, find the first server. And this one small change is what makes the whole system resilient to servers being added or removed. Let's actually see that happen next. Now, let's do the thing that broke naive hashing. Add a server and watch what happens on the ring. We drop server D onto the ring right between server C and server A. With naive hashing, remember, this would have remapped nearly everything. But on the ring, only the keys that fall in the small arc between server D and its predecessor need to move. Every other key still pointing to the exact same server it always was. That green dot is the only key affected here. It used to belong to server A, now it belongs to D because D is closer going clockwise. This is the headline benefit of consistent hashing. On average, adding a server only remaps about k over n keys, where k is total keys and n is server count, not 75%, a tiny proportional slice. That's the difference between a routine scale-up and a production incident. Same idea, but now let's crash a server instead of adding one, because in the real world, servers fail way more often than you'd like. Server B goes down. What happens to the keys it was holding? They simply fall through to the next server clockwise. In this case, server C absorbs them. Server A, sitting on the other side of the ring, doesn't even notice this happened. This is huge for availability. In a naive hash mod n system, losing one server changes n, which reshuffles almost everything at the worst possible time, while you're already down a server. With the ring, failure is local. Only the failed node's immediate neighbor picks up the slack. That's exactly the kind of graceful degradation interviewers want to hear you describe. So the ring solves the rebalancing problem, but it introduces a new one, and this is the part a lot of tutorials skip. When you only hash a handful of servers onto the ring, their positions are essentially random, and random points on a circle are not evenly spaced. Sometimes by chance, three servers end up clustered close together, leaving one giant empty arc. Look at this ring. Server A ends up owning this massive stretch while B and C are crammed next to each other, barely getting any keys. In production, that means server A gets hammered with way more traffic and way more data than B or C, a hotspot sitting right next to underutilized machines. So, great. We fixed the rebalancing problem, but now we have a load balancing problem. This is exactly the kind of nuance that separates a candidate who memorized hash ring good from one who actually understands the trade-offs. So, how do we fix it? The fix is called virtual nodes or vNodes, and honestly, it's one of those solutions that's almost embarrassingly simple once you see it. Instead of hashing each physical server once onto the ring, you hash it multiple times, 100, 200 times, using slightly different identifiers like server A1, server A2, server A3, and so on. Each of those becomes its own point on the ring, but they all still route back to the same physical machine. Now look at the ring. Server A, B, and C are each scattered as many small points all around the circle instead of one single spot. And with that many points, the law of large numbers kicks in. The arcs even out. In practice, real systems use something like 100 to 200 virtual nodes per physical server, and that gets you under 5% load variance between machines. And this is exactly where most candidates leave points on the table. They say, use consistent hashing and stop right there. Mentioning virtual nodes unprompted is a strong signal in an interview. Now, here's the layer most YouTube videos on this topic completely skip. And it's exactly the kind of thing that shows up in 2026 level interview loops, where interviewers are grading for depth, not just the textbook answer. Virtual nodes solve structural imbalance, meaning they make sure each server holds roughly the same number of keys, but they do nothing about traffic imbalance. Imagine one specific key, say a celebrity's profile or a viral product, suddenly gets millions of reads per second. Consistent hashing still sends every single one of those requests to the exact same server because that's the server that owns that key. Doesn't matter how many virtual nodes you have. So real systems layer on additional strategies. Read replicas. Replicate that one hot key across multiple servers and load balance reads across the copies. Or key salting. Append a random suffix to the key, like username -0 through 9, so it's effectively spread across 10 different ring positions, and you aggregate the reads on the way out. If you can articulate this distinction in an interview, structural balance versus traffic balance, that alone puts you ahead of most candidates. This isn't some academic exercise you'll never touch again after the interview. This is running underneath systems you probably use every single day. DynamoDB uses it to route requests based on partition keys at massive scale. Cassandra's entire data model is built on a token ring, which is literally consistent hashing under a different name. Redis cluster does something conceptually similar with hash slots. CDNs like Akamai use it to route your request to the nearest edge server without needing a giant centralized lookup table. Riak, a distributed key value store, same idea. Even some load balancers use it under the hood for sticky sessions. So a user keeps hitting the same backend server without the load balancer needing to track every single session centrally. So when you explain this in an interview, Don't just explain the algorithm. Mention one or two of these real systems. It shows that you understand this isn't textbook trivia, it's infrastructure you'd actually be building on. All right, let's bring it all together. Here's your interview ready summary. 1. The problem. Naive modern hashing remaps almost every key when your server count changes. 2. The fix. A hash ring where only roughly k over n keys move when a server is added or removed. 3. The catch. A plain ring can still be unevenly loaded with few servers, and virtual nodes fix that by giving each server many points on the ring instead of one. And 4. The part that'll actually set you apart. Virtual nodes fix data balance, not traffic balance. If you can casually drop in a mention of hotkeys, read replicas, or key salting, you're no longer sounding like someone who memorized a diagram. You sound like someone who's actually thought about running this in production. That's consistent hashing, fully broken down. If this helped you build real intuition instead of just memorizing the ring picture, that's exactly what this channel is for. Follow for more such content, and I'll see you in the next one.